Welcome back. We start lecture 8 today for the course Corrosion Failures and Analysis. Lecture 8 and topic will continue discussion on galvanic corrosion. And if we summarize what we have done in lecture 6 and 7, if you recall that in lecture 6 we talked about several possibilities that even if we have the same metal or the same alloy surface, we do get galvanic effect, and due to difference in concentration of active species, due to stress effect, one section could be highly stressed, one section could be least stressed, and then a highly stressed section might get corroded. Then we could have a situation like local concentration change of the alloy, like what we experience in case of 18-8 stainless steel, where chromium depletion happens across a grain boundary and that lead to intergranular corrosion. So, that is also there. Also we have galvanic effect. Even you would see later that crevice as well as pitting corrosion, we have galvanic effect. The pit portion is specifically anode, even the crevice portion is specifically anode, around that area will be cathode. So, for the galvanic corrosion, we have to see that this particular condition should be met: preferential cathode and anode area. Okay, so, this is very important in case of galvanic effect. It need not be, for example, of course, as per the common definition we say that it is a two metal corrosion, where two different metals are electrically connected, and then if we expose that electrically connected two metal component into an electrolyte, the active metal, which is anode area, dissolves, and cathode, which is noble metal, which is protected. But it does happen in other cases where it is the same plate, where two metal condition does not exist. Okay. So, for example, one example, if you recall, that I wanted to show you, that if it is a stressed condition, then the corrosion happens on the stressed part because of the galvanic effect. So, one example let me just show you. So, if you this particular component, so this is a bent rebar, which is reaped rebar. Okay. So, if you see that this bent portion, this portion as well as this portion, they are specifically corroded. Red rust is more in those cases, these two segments, because whenever you bent it, that particular portion experiences more stress, and that leads to differential cell formation. This particular part would be preferentially anode, and the rest of the part which is not bent will be preferentially cathode, and that leads to a galvanic effect like this. Okay. So, this bent portion, if you see, it is more reddish rather than the rest of the portion. The rest of the portion also we have corrosion, but not that pronounced if we consider the bent portion. So, this is one example I just wanted to show you. Now, interestingly, if you see that this is the same metal part, there is no different metal parts joined here, but still we do experience galvanic effect. Now, coming to the experiment, the virtual experiment what we have been doing, if we see that there are three parts. One is first experiment what we did, we have a HCl medium, and there we have dipped zinc, and we have weight there. Okay. Another experiment, we had iron as well as zinc, same area. Let us say this is iron and this is zinc. So, this is a two metal contact, and in the two metal contact, and we also measure the weight here, and we could see that here also weight is reduced, but the majority of the weight loss was basically coming from the zinc surface, and the corrosion pattern, if we see that, it is like this. And iron also do get corroded some portion, and zinc would be more, but the corrosion would be more close to the joint rather than away from that joint. Another experiment we did, same HCl medium, we had iron block and we measured the weight, and we saw that weight is lost. Now, if we all are HCl, an observation what we had in this case, hydrogen bubble preferentially formed on iron surface, you do get hydrogen bubble, but if we consider zinc surface, not much of hydrogen bubble. But these two cases observations would be almost similar, lot of hydrogen bubble, here also hydrogen bubble. And interestingly, it might be possible that the corrosion rate Cr, and here also Cr, if you compare zinc and this is iron, this would be might be less than corrosion rate of iron. But once we join them, we see that the corrosion rate of zinc in this coupled case is very high as compared to corrosion rate of iron. And the last observation what we had is basically initially to start with, the bubble will form on both the surfaces, but gradually you will see, rather quickly you will see that the bubble only will form on iron surface, not on zinc surface. And in this case, iron becomes cathode, zinc becomes anode. And in this case, and that is what you have preferential zinc corrosion, in this case, and in those cases you will see uniform corrosion. Uniform corrosion. And if we try to see the reactions, governing reactions, you would see that in this case you will see these two reactions, and here these two reactions. And if we see the center part will have but this, the rate of this reaction would be very small compared to the rate of this reaction, but you would actually experience iron dissolution also. Now, interestingly, the cathodic reaction, if it is pure HCl and that to deaerated, so that means there is no dissolved oxygen, So, the cathodic reaction would always be this one. and in this case anodic reaction, more of anodic reaction would be this, less of anodic reaction would be this. Now, here you could see that though they are individually dipped in HCl, both are acting as anodic, it is a very highly corrosive situation, and both the metals would dissolve at a very high rate, but once we join together and expose to HCl, iron dissolves less, zinc dissolves more. So, that is what this is a typical example of galvanic corrosion. Let us analyze this part little more with the help of mixed potential theory, and in order to understand mixed potential theory, you have to go back and try to check my other videos on galvanic corrosion, on mixed potential theory rather. So, there also I have explained the same concept, but I am just in brief repeating the same thing, okay, just to analyze this virtual experiment. So, if we consider zinc case, so this is exchange current density on the zinc surface, and I am considering, this is an assumption, but it should not be true value. I am assuming that this is starting with its standard reduction potential, both the cases, just to analyze this part, but this value would be different, this value would be different depending on the pH of the solution. Okay. Now, in this case, if you see here also it will be same like this, on iron surface. And here this is my I core and this is E core, this is E core and this is I core, and let us say this is log I, this is log I, ampere per centimeter square, this is ampere per centimeter square. And remember, we are taking 1 centimeter square area metal. In all the cases, and we know this value is 0.76 volt, and in this case this value is minus 0.44 volt. Okay. Now, we have to put them on this scale. So, this is log I, this is E. So, this position does not change. So, this is, let us say this is I 0 hydrogen on zinc surface, this is I 0 on iron surface, and if I see the position of this is E 0 Fe, and let us see it is here. This one, and here it is This is individually they are like this. So, this is for iron, this is for iron individually, and this is zinc. Now, once we have mixed potential, so we have to consider this concept, the total okay. So, now if you see this, let me drop it little more bit. That is what you have to practice it. Okay. It is very important to practice. So, now here you have to add this hydrogen reduction reactions, and you have to also add the total metallic oxidation. So, here it is meeting. So, it will go like this. Okay. So, now this is the part core mixed. Core mixed. Now, if you want to know okay, what will be my corrosion rate of iron as well as zinc after consideration of mixed potential for the case where both the iron and zinc plate blocks are joined together and placed in HCl. So, you just need to draw a line here from here okay. And at this point you have I on iron surface hydrogen reduction should be plus I on zinc surface hydrogen reduction should be equal to I of iron plus I of zinc, and here it is A. I am just putting A because A is anodic, and here I can put C. The C is cathodic. Okay. So, now total cathodic reaction rate is equal to total anodic reaction rate. Now, we have to see across this red line, that red line wherever it cuts the anodic line of zinc. So, this is the anodic line of zinc, where zinc minus 2 equal to zinc plus ions are forming, and that point is this one. Now, you could see that previously the corrosion rate of zinc was individually what is here, it was here, which is I A zinc when it was alone, not coupled. Okay. But after coupling, you see the corrosion rate of zinc, it is at this point, which is I so this point is I A zinc when coupled. and if we consider the corrosion rate of iron before coupling, it was here. So, this is I A iron not coupled, and after coupling the corrosion rate of iron is, because this is the line which talks about anodic reaction of iron. So, the corrosion rate of iron is now, this one is the corrosion rate of iron after coupling. So, this is I A iron coupled, and of course, this line is nothing but cathodic reaction lines. This is hydrogen. Similarly, these two lines are this and this. Now, interesting part is, let us see. So, that means it is very clear that I A of zinc, when it is coupled with iron, has gone up I A zinc when not coupled. As well as I A iron when coupled with zinc is less than iron not coupled. And if I compare, so that means first the observation what we had, that once we join together, iron corrosion rate would reduce to a drastic level and zinc corrosion rate will increase to a drastic level, and interestingly exactly it happens like that. Now, question is, in order to another observation what we had was that IC of hydrogen on zinc surface when coupled with iron should be less than IC hydrogen on zinc surface when not coupled. Let us see whether that condition satisfies. Now, if I see the hydrogen evolution reaction rate when it was not coupled for the zinc case, it was here. So, this is that round part, this part is basically IC hydrogen on zinc surface not coupled. And let us see what is the hydrogen evolution rate on zinc surface after it is coupled with iron. So, again that red line you have to see, this particular line you have to look at, and you have to see where that line cuts with the hydrogen reduction line in case of zinc. It is cutting here. So, that value is nothing but IC hydrogen on zinc surface when coupled. So, definitely this value from here to here it has got reduced, and remember this is in log scale. So, that is what the reduction is quite large. So, this condition is met. Now, let us see the another condition observation was on iron surface the hydrogen evolution rate would increase. So, that means the statement is I see hydrogen on iron surface when coupled with zinc should be greater than I see hydrogen iron surface when not coupled. Let us see those 2 points. Again we have to see the red lines, and the red lines, if I see, it is cutting the hydrogen line for the iron case, this here. Okay. So, this is I see hydrogen on iron surface coupled, and let us see what was the I see hydrogen on iron surface when it was not coupled. So, that point is this point, which is I see hydrogen iron not coupled. Okay. And interestingly, those 2 points not coupled cases are shown here. So, which is again mixed potential theory, because the total reduction rate should be equal to total oxidation rate. So, here also this is matching. So, that means preferential, and what is the cathodic reaction in both the cases? This is the cathodic reaction. So, cathodic reaction is preferentially taking place. Hence, this is cathode. Since we know that cathodic reaction takes place on cathode, and in this surface, on this surface, hydrogen evolution reaction is very less, but zinc dissolution is maximum on this zinc surface. So, this is zinc surface, and that is what it is anode. An interesting part is we could also see that hydrogen evolution on the zinc surface is less. And another important thing is, whenever we say galvanic corrosion, it does not mean that the cathode does not corrode, cathode also corrodes. Here you see cathode also corrodes, but it is negligible sometimes, but negligible or very small. Fine. So, that means with the mixed potential theory we could analyze the entire these 3 virtual experiments, and interestingly it is all matching with the theory, and we could see that 2 concepts. One is one part becomes preferentially cathode, another part becomes preferentially anode, and cathode also corrodes, but at a much smaller rate, but the anode corrodes at a much higher rate. And here the major, one of the important conditions what we have imposed here, remember that will come for the discussion, is same area. We will see if the area changes for cathodes and anodes, we will have a serious implication on galvanic corrosion. So, let us stop here. We will continue our discussion on galvanic corrosion in our subsequent lectures, and remember we will explain galvanic corrosion quite a deep, because you will see the subsequent lectures whenever galvanic corrosion, whenever any type of corrosion forms comes in, we will see the galvanic effect needs to be considered. So, let us stop here, we will continue in our next lecture. Thank you.